Hi there, welcome to the session. This is Steve Webb, specifying green and embodied carbon. I'm Christine Murray, I'm the director of the Festival Place and editor-in-chief of The Developer. It's my great pleasure to invite you here today. First up, I'm going to give you a little micro tour of Airmeet in case this is your first session at the festival. So first of all, there's a happy face below me. So if you've got some, you can click on that, you can send me some emojis. Do you want to give that a try? See if you guys can send me. Thank you very much. That's very nice. Good. Thumbs up and a heart. That's right. Speakers really love this because it can be quite alienating when you're presenting up here and you don't actually see your audience. So do send emojis when you like something that was said, if a light bulb moment, or just a thumbs up to keep them going, keep the energy going. So thanks very much for that. Next to that, you've got a hand in the Q&A session if you would rather deliver your question or your comment to Steve in person. We ask you to keep it succinct, but you can raise your hand and I can add you to the stage. Many people are really scared to do that, but you know what? It's a really great thing for us to come together, a really great opportunity to meet some of you guys as well. So do consider putting your hand up. Other than that, over on your control panel, which is over the session description, you've got attendees, you can see who's here. You've got your chat, so you can comment and put your comments in there and have a discussion as an audience group. And below that, you've got your questions. When you click on the questions tab, you need to select this session, so Steve Webb, specifying green and embodied carbon, and then you can put your questions in there. For Steve, we'll be taking some questions after his talk, and I'll be back to host that. And now I'm just going, it just leaves me to introduce Steve Webb, director of Webb Yates. Steve founded Webb Yates Engineers with Andy Waits in 2005. He started his career as a site engineer for the Jubilee Line extension, gaining firsthand experience of site issues and subterranean construction in London. He went on to work at Whitby Bird and Sinclair Knight Merckx in Santiago Calatrava when he worked on projects including Wembley Arena and the Turning Torso Tower in Sweden, a 58-story residential tower with a twisting form. That's actually a tongue twister as well, the Turning Torso Tower. So thank you for warming me up there this morning, Steve. He's interested in combining imagination with technical rigor to create inventive structural designs. And he's also pioneered the practices approach to innovation and sustainability, encouraging the use of non-conventional materials from cast iron to cork and from inflatables to stone to design low carbon and environmentally conscious buildings and structures. So Steve, I'm going to hand over to you now. Really looking forward to your talk. Welcome to the festival.
Thank you very much. Hi everybody, thank you for coming.
Send him an emoji encouragement as he finds his share screen.
Let me share my screen.
There we go.
Emojis. Can everybody see that?
Yeah, we can see it perfectly, Steve.
Okay, good. As Christine said, Webb Yates is predominantly structural engineering and building services. We call ourselves transdisciplinary rather than multidisciplinary, because we try and understand each other's disciplines and we try and work across both types of engineering within buildings to get slightly more rational designs. We work at all kinds of scales. So we started off quite a long time ago doing back extensions and MOF conversions, and we still do little projects like that, but we also do big infrastructure projects. The project on the right here is underground baggage handling, transit train projects at Heathrow Airport. So we work across quite varied scales. So I think, I'm not sure whether my presentation matches the description of this talk particularly well in terms of specifying green, but what I wanted to talk about really was was what we can do, particularly with structures, to reduce embodied carbon. So I think previously, when buildings weren't particularly well insulated and building services systems weren't very efficient, the bulk of energy that a building used was in heating over the life cycle of the building, and people haven't really focused on the energy within the building itself. But actually, now that buildings are quite well insulated and building systems are quite efficient, actually the structure of the building is more important in terms of its embodied carbon. So when we talk about embodied carbon, we're talking about the carbon dioxide that's released by the processes that produce the materials that you build with. A building, an office building is thousands of tons of material. So choosing what we make that with is really important. The primary element of that is actually the structure, for the far greater part by volume and by mass of what we're building. So there are resources for working these things out. So there's the Bath Carbon Inventory, for example, which has a big list of different building materials, and it's got the carbon footprint for each of those materials. There's a website called OneClick where you can calculate these things. We have carbon guardians, we call them. We have algorithms for calculating from Revit models what the embodied carbon for different building options are. But what I'm and people are constantly craving information and ways of calculating this, but what I'm advocating is more we just kind of think a little bit more laterally about what we're doing and the choices we're making. So this slide is showing forestry, wood production on the top and steel production underneath. I don't think we need a website or a guide to work out which of these two activities is better for the environment. We try to, as a rule, offer different solutions for all of our projects, and we look at what the way that buildings can be built as an alternative. But we were interested. Steel is obviously quite bad for the environment. Timber's quite good, but steel is much stronger, so you use less steel. So there's a kind of swing and a roundabout in terms of in terms of evaluating these things. So this slide was a little exercise that we did to work out what's most effective in carbon terms. So these are all beams to carry a 1-ton car across a 2-meter gap. So on the top row, these are structural sections. They're all strong enough to carry that car. And on the second row, they're all the same stiffness. So you can see here, post-tensioned stone, which we sometimes use. It's a very thin sliver of stone. These aren't sections that we would actually use. These are a kind of pro rata at equivalent depth. A 100 by 200 millimeter piece of softwood is strong enough. Skinnier pieces of hardwood and engineered timber, 28 millimeters of concrete, and 2.1 millimeters of steel. So 2.1 millimeters of steel is enough to do that. So that, as I said, that section won't really work, but on a pro rata basis, that's all you need. On a stiffness basis, the most structural elements are designed are inherently strong enough, but they need to be stiff enough, and the stiffness is the primary criteria. 5.1 millimeters of steel, 100 millimeters of concrete, the same for the timber, 40 millimeters of stone. On the bottom row, these are the carbon footprints per meter for each of those sections. So you can see the steel, 22 kilograms per meter run. The concrete's about 15. The timber's about 5, with minus 16. The minus 16 is embodied, or I should say sequestered carbon in the tree. When the tree grows, it consumes a lot of carbon dioxide, and that carbon is locked into the timber. So when you grow the tree, you lock that up. If you burn your building at the end, or you bury it, and that carbon escapes as methane, that's actually quite bad for the environment. So the negative green is kind of sort of debatable. You can see the stone has very low carbon, but no sequestered carbon in the way that the trees do. So if you really want to help the environment stay, you would use timber. There's been a lot of publicity about the badness of concrete. We were talking to an architect recently who said that he realized that concrete was really bad for the environment, so he built a steel building instead. And steel is even worse. It's like saying I gave up cocaine and took up heroin instead. It's really makes a huge difference to to use timber or to use stone over concrete and steel. Really, I think we were working out, people in my office, their personal carbon footprints are about 10 tons per year for their holidays and cars and houses and all kinds of stuff. But the things that they specify at their desks, the buildings that they design, hundreds, if not thousands of tons of carbon dioxide. So we think it's morally important to try and make as many of our buildings as possible out of timber or out of stone. So I was going to show you a few examples. This is York House in King's Cross, a project that we finished recently with DMFK Architects. This was an existing 1980s building, so you can see the existing building there. We did a front extension and a roof extension. Extensions, after quite a long kind of battle with the contractor, the extensions were all timber. Front extension is a CLT structure. The roof extension is a CLT structure. Timber, the use of timber in buildings become kind of synonymous. The word CLT has become like Hoover, you know, that it's synonymous with a product. Actually, timber doesn't have to be CLT. CLT is one solution. But we were quite pleased that we were able to make all of those elements timber on this project and cut out a lot of CO2. The facade in this case is brick. Brick's not good for the environment, but contextually that's what it had to be here. The facade is corrugated in order to make it stiffer, to make it capable of standing independently on the ground and not need to take support from the building inside, which meant that the timber frame didn't have to support the brickwork. This is a project we're working on at the moment, much bigger one with Field and Clare Bradley. It's a £25 million office building in Battersea that just got planning permission. This again is a big CLT office. In this case, the CLT was a little more expensive than the concrete and steel alternative, but actually when you remove the decoration, the prices were quite similar in construction terms. There was an issue related to acoustics. So the acoustician was saying that the mass of the timber wasn't sufficient to provide VCO level acoustic separation between floors. So as a consequence, we had to put treatment on all the floors and we had to put isolating pads on all the pedestals on the floor. So quite an expense. In fact, $500,000 of acoustic treatment was required to allow this to be a timber building. We were thinking that was quite, this is very problematic and this is going to make the client decide to reverse his decision to use timber and to go back to steel and concrete. And we were kind of interested in how timber really performs. Timber's lighter than concrete, so acousticians, make the assessment that it's less acoustically resilient, but it also has higher damping, and that's the thing that's quite difficult to quantify. So we were able to arrange for our acoustician to go back to this building. This is a 300 millimeter CLT slab. It's got a raised floor on top of it, no other acoustic treatment, and a bare soffit. So they went and tested that, and they found that this actually complied with the BCO regulations without any treatment at all. So the fact that we had this building as an exemplar and were able to test it, the development of this building means take away £500,000 worth of acoustic treatment and retain timber as the solution for the scheme. So I think that was quite an important bit of information discovery from the earlier job. As I said, timber doesn't have to be CLT. There are lots of ways of building timber, not always CLT. So we had a small project many years ago with Punor and Prasad for Wimbledon College of Art. And they were our M&E engineers, or our director of M&E was the M&E engineer on this project, which is where we met. And he had said that if the building had good thermal mass, that he wouldn't have to do any air conditioning. So the design of the building is based around passive house principles. Lots of insulation, air tightness, but it needed thermal mass. So the initial scheme for the building had a series of steel portal frames and big concrete slabs. So we were kind of challenging him or discussing with him, how much concrete do you really need for thermal mass? Does the 300 millimeter slab change temperature during a daily cycle of usage, or is it only the surface? And so we did some experimentation and some testing, found that actually 50 millimeters of concrete was enough to passively condition the space. So when I say passively condition, What I mean is if you have hard, heavy surfaces inside the room, in the daytime when the room gets really hot, the heat is absorbed by those hard surfaces. At nighttime, you can open all the windows and those pieces of structure can cool down again so that they're fresh in the morning for the next day, which means that you don't have to have air conditioning, which is a big saving both in energy and money. So our solution here was to build a timber frame. So the whole building is completely timber, but the floors are made of 50 millimeters of concrete, which is exposed inside the building. So this is the upper floor of that building. The roof trusses, so concrete on top of timber. So when these people create heat, the heat's absorbed by that concrete up there. It's quite unusual kind of combination of material to have timber supporting concrete rather than the other way around. And normally you don't see the two materials in combination. So this is the same on both floors of that building. This is very successful. This building has a negative carbon, negative embodied carbon. It's got PV cells on the roof, so it actually exports electricity to the grid. So it's a net producer of energy rather than consumer. Obviously, there's a lot of CO2 sequestered in the timber. So we took that principle to this next building, which is the Anna Freud Centre, also with Panora and Prasad. This is a £17 million office building. There's a huge concrete basement under here, which isn't sustainable at all, but all of the buildings on top are either reused Victorian warehouse on the left-hand side or new timber frame in front and on the right. So here we're building a timber frame using Baubucher. In Germany, there was an oversupply of beech. I didn't really know what to do with it. So I started laminating it into structural beams. This timber is very, very strong. It's GL 76, which means it's got 76 newtons per millimeter squared. Very, very strong timber and very stiff. So it has a stiffness value of about 16,000 newtons per millimeter squared, which is similar in the long term to most reinforced concrete. Here we wanted to use the concrete floor in the same way to provide passive conditioning and to remove air conditioning from the building. But this time we made the concrete composite with the timber. So you can see in this shot, they're lifting in that concrete beam. There are gaps between the pieces of concrete with stitching. We put coach screws, I'm not sure why I'm showing it here, coach screws onto the tops of those timber beams so that we fill that gap up with concrete, which means that when the beams flex, they get compression strength from the concrete. So the concrete and the timber work compositely together. And we have a largely timber frame, very small amount of concrete, no air conditioning. See this being erected. That's the finish on the underside. So all of that's exposed inside the building. You can see it, and it's kind of, I mean, these are both examples of where combining the building services approach with the structural approach. And I'm not saying that the two people necessarily need to be in the same company, but they're getting those things to work together. So the building inherently has just the right amount of mass to avoid needing to be excessively cooled. It's rational. The other thing that I'm quite interested in is, so we're looking at a high-rise building. I think we're looking at a 15-story building in West London with Tony Fratton, and we were looking at, so timber obviously has certain disadvantages. There are new regulations, fire regulations related to Grenfell Tower. It's kind of, the Grenfell thing has repercussed quite strongly against the timber industry, and it's surprising that a problem with a concrete building has such a big impact on timber buildings, but people are very concerned with all buildings, fire protection, fire design. So there's a ban on residential buildings over 18 meters with timber or flammable materials in the facade, which is affected timber. It's also true that on very tall buildings, timber is flexible and it shortens under axial load. So we were thinking actually a good combination is a hybrid system. So the hybrid, the two projects I was showing before are effectively hybrids. We're using concrete, small amounts of concrete in compression and more timber in tension. So another way of combining those two materials is to have the vertical structure in a tower and concrete for thermal mass and passive conditioning, and the horizontal structure in timber. The biggest volume of a tall building. So the scribbles that I've got there, a 20-story building, 30 by 15 meters. The RC, 3,000 meters cubed of concrete with the hybrid. So for a totally concrete version, there would be 3,000 meters cubed. For a hybrid version with timber floors, so CLT floors, concrete walls, concrete cores, you'd have 2,250 cubic meters of timber and 500 of concrete. So with the hybrid version, you're using concrete in compression where you need it, where it's really strong. You're getting passive conditioning from it, but where the bulk of the mass is in the floors, you're swapping it out for CLT. The typologies of CLT in terms of big panels being lifted in, big concrete panels being lifted in, very similar. They're just different companies. And actually, when we approached CLT companies and said, would you be happy to work hand in hand with flat concrete panel manufacturers, they were very happy to do that, and, because the erection sequence is very similar. So that mixture of materials is quite effective for that kind of thing. This is a hybrid building that we did in Upper Street with Taha. This is a 3D scanned CNC molded concrete version. The building on that site was bombed, but the building on the opposite corner of that terrace of shops was still there, so we were able to take a copy of it. So in this case, it's a concrete twin wall facade with timber floors. The hybridization of timber and other materials is if you have two subcontractors that are really happy to work hand in glove, then that's ideal. But actually, quite often you get subcontractors that don't want to share a site, and you can get a mix of responsibilities and conflict. So actually, having the ability for one person to come in and build their bit out, somebody else to come and do their bit after was quite good. So in this case, the timber frame was built completely on temporary struts. So all of those diagonals and verticals are just temporary. The concrete frame was then cast around it afterwards, and then finished. The timber's exposed on the inside, and the concrete frame is finished afterwards. So that kind of methodology allows you to separate the two contracts. Timber. So timber is, was quite available today, feasible for most projects. There are lots of different manufacturers. There are lots of different types of timber products. So it's quite easy to have a sensible procurement and to use timber instead of concrete. Less well known or less commonly used is stone. So we work quite a lot with stone, and I think stone has a lot of potential to be a solution to embodied carbon for many buildings. Stone is hugely abundant and very, very strong. This is a limestone mine quarry in France, where they're cutting out big blocks of limestone. Typically, we take in the construction sector today, we take a 200 Newton strength block of limestone. So limestone is kind of naturally very strong, 100 to 200 Newtons. We crush it. We get a lot of gas. We burn it to make cement. We batch it up with fresh water, which is pretty limited, and also sharp sand, which is limited. We reinforce it. We put up formwork and false work. We do all the other things involved in concrete, vibrate it, releasing agent. We end up with something which is 40 Newtons. The complexity and the logistics of concrete production are far more complicated than stone. If you looked at it in the round, why on earth wouldn't you just use the stone under your feet? Why would you go around going through all these processes to make something which is an inferior product? I think this is just a result of a chain of events in industrial development. People were saying, why is stone sustainable? Well, if you gave every person on the planet a 5 by 5 meter piece of 200 millimeter stone or concrete slab, for example, 7 billion people would be 35 cubic kilometers, which would be 20 meters deep, 42 by 42 kilometer quarry, a single quarry that size, which is a speck compared to the volume of stone that's available it's a heap of stone about the size of Ben Nevis. All current construction products are mined. So obviously steel is mined. Iron ore is about 1.5 times bigger in volume than the steel that it produces. Concrete is mined. Everything comes out of the ground at the end of the day. And actually the volumes of building are very, very small compared to geological volumes. Comparing stone to timber, for example. I mean, I'm not trying to set stone against timber, but actually, a tree sits in a 5 meter square plot. The tree has a strength of about 7 newtons and has about 1.5 cubic meters of material and takes 25 years to grow. So the tree on top, 25 years, you get 1.5 cubic meters of something with a strength of 7 or 8 newtons. The stone underneath the tree, in this case, 5 by 5 meters, say 20 meters deep, you're getting 500 cubic meters of stone, and the strength of the stone is about 150 newtons per millimeter squared. The tree takes 25 years to grow. To quarry that amount of material probably takes 3 months. So you can see that per year, per hectare, useful building material, far more powerful to make a quarry than it is to make forestry. And although forestry is clearly much better for the environment than steel production, actually monocultural pine forests are not very good for the environment. And if you look at an aerial map, for example, of Edinburgh, Edinburgh is largely a stone city. The quarry that produced most of Edinburgh is underneath Sainsbury's car park, which you wouldn't even notice. Whereas if you look around the Scottish countryside, there's a lot of commercial forestry. It's not really that pretty. So extracting stone is quite good. Good way of building. So coming back to this diagram again, the reinforced stone was something like 1.5 kilos of CO2 per meter. The reason is you take the stone, you cut the stone out of the ground with a wire saw, which requires very little power, you transport it to site and you use it. There are very few processes in its manufacturing. It's already made. Stone is generally much stronger than concrete. It's stronger in tension and it's stiffer. So we use smaller amounts of stone than we would in concrete for those reasons. We put less reinforcement in it because it has a higher tensile strength. Stone is a naturally occurring material. As an industry, stone production is massively underinvested in, so they don't have very sophisticated stone grading procedures. We have to take samples from the stone that we're using. We take quite a big factor of safety against things like that ammonite, which are invisible in that sample, or which was invisible in that sample, and reduce the strength of the stone in that case quite a lot. If there's a future for stone, it's definitely going to be related to improved methods of grading. We started working in stone as a company. We started off making fake stone staircases with wood. So this is a traditional stone stair. The way that the stair works, so the tread above bears on the tread underneath. The stone treads don't cantilever, so they call this a stone cantilever stair. It doesn't cantilever. The stone sticking out of the wall, if you jumped up and down on the end of it, would lever itself out with a brickbat very easily. What really happens is the stone above pushes down on the stone below, which is supported on the stone below that. The tread in between can't twist out of the way because it's built into the wall. So this is a kind of strange mechanism that allows you to build those kind of staircases. So we did some timber versions of these. So this is a plywood version fixed to a 50 millimeter thick terracotta wall. We did oak versions and other plywood versions. We started doing stone, traditional, both traditional and non-traditional. This is with Glen Howells, where we've cut away the stone that's not carrying very much stress, and this is a version with Amin Taha quarry finish on the side of that, but otherwise it's a totally traditional stair. The wires there are just to stop people from falling through the balustrade. But our stonemasons were limited to selling stairs to people who have that kind of configuration where you have a flight adjacent to a wall. So they were really interested in making free-spanning stone elements. We started experimenting with how we could reinforce stone. We're not the first people in the world to do this, but it's not really codified, I have to say, so we had to kind of make calculations. In this case, we're post-tensioning 4 50mm paving slabs to span 3.2 meters. There are 2 8mm cables running through there on a parabolic trajectory, so the tension in the cables lifts the stone. So we were able to span 3.2 meters with those 50mm thick slabs. So very thin, very effective, very strong. We've been working in R&D. This is Wendell Sebastian from UCL, who's our kind of partner in the R&D work that we're doing with this. So we're doing a lot of testing of stone beams, how we can reinforce them, how we can grout them together. We can do this because the stair market is pretty fancy, and that these stairs are quite high cost. So people pay good fees, and inherent in those fees, there's money for R&D. So this was a staircase. We did kind of short, straight stairs, slightly curved stairs, and we kind of built up to this one. We developed an analytical method for working them. We did a lot of testing. Some of the testing failed, so you can hear there's a stressing order problem, and the stone failed quite abruptly, but eventually we got it working. And so this was kind of our first really big post-tension stone stair. It's bigger than it looks. It's 1.4 meters wide, the treads, and it turns through 270 degrees. There are 2 12mm cables inside there with 12 tons of pre-stress in each cable. So we're kind of starting at this end of the market. I think it's kind of ironic that we're doing quite complex things when really what we want to be doing are very simple things. So we can make the stair work because somebody's willing to pay for it and they really want that resting feature in their house. Whereas actually, I think doing simple beams is much easier. We're also looking at unreinforced stone. Gothic cathedrals, for example, are unreinforced stone structures of big spans, incredibly mathematical things that we can, that I think we would struggle to emulate today, even with quite sophisticated analysis tools. So this was a staircase that we were designing in central London. It was initially going to be a steel stair clad in stone, and then a post-tension stair, but we decided we'd try and make it unreinforced stone. So we experimented with styrofoam model. We were convinced that if we could make the styrofoam model stand up, even though it's quite light, then we'd be able to make the real stone thing stand up. So we used that as an experimenting tool, developed this system, designed this there. So this stair has no steel or reinforcement in it of any kind. It's just stone. There's an arch on one side over here. There's a kind of torsional interlock between the treads, which means that one stone can transmit load to the next. So it's quite interesting what you can do without reinforcing stone. In this case, it's sat on the 5th floor of a 1920s building with a 6-inch slab, so we had to do something to support it in the depth of the floor finishes. The stair weighed 16 tons, so it's quite heavy. We built this upward curved steel waffle plate, so that when the weight of the stair was set on it, it just sat flat under the floor finishes. This was a similarly unreinforcing sculpture with Anthony Gormley, polystyrene model method again. This was supposed to last for 200 years and be demountable and rebuildable, so it took us a long time to figure out. It's very difficult to hide steel fixings and things in there, so we were trying to work out how the stones can sit together in order not to collapse. So, for example, this stone here sits just over the back of that one, which takes weight from this one. There's a kind of mensura inside here from these two stones that are held together by that. So kind of balancing stones, building them in a particular order, if you put two flat faces of stone together without any kind of bedding or without mortar, they naturally rest on 3 points or rock. So it's quite important. So we needed to know really where the forces were going. So we These Lego nipples, 3 Lego nipples per stone, so that we know exactly where each stone is bearing. And then this is our first kind of biggish stone building. This is the Amin Taha project in Clerkenwell Close. It's a 6-story concrete frame, so concrete slabs and a concrete core, but no columns. So the building was built similarly to the timber one, built and left on props. So the concrete frame went up quite quickly and then followed the stone. Stone facade is completely load bearing, holds all of the floors up. You can see these thermally broken connections cast into the edges of the concrete. The stone is built, the stone is sized according to its load, so it's skinnier on the corners, for example, where it doesn't carry very much load, and it's kind of fatter in the middle at the bottom. There are 3 finishes here. So Amin went to a quarry and he saw the way that they were cutting the stone. So they drill and wedge, and then they split the stone from the bedding, and then they cut it. So rather than spend money refinishing the stone, he left those finishes in the finished thing. So they kind of arrived at site the way they were cut in the quarry. And yeah, so the stone's completely load bearing. So I think this building itself, stone clearly has less CO2 than the concrete columns would have had. If we'd done a stone cladding system, there would have been far more cutting and far more cladding support. So there would have been a lot of steel, a lot of layers and stuff holding up the cladding. Actually, the simplicity of just building with solid stone saves a lot of time, saves a lot of trouble. And I think people really, there was a kind of mixed response to this building, but a lot of people I know, when we would explain to them, it's a load-bearing facade. It's not just capricious decoration. It's actually intrinsically part of the structure of the building. They changed the way that they felt about it. They kind of thought it was more valuable. And then this is more recently, we were asked to do an exhibition at the V&A, Engineering Yates. We were interested in what you can do without reinforcing stone. So obviously vaults and Gothic things are all very nice, but actually they're not much use in an office building. So we were kind of curious to see what we could do with stone flat. So this is rather like a plastic Mickey Mouse tile puzzle. Each of these is a 500mm stone, Mirabel Portuguese marble. It's supported around the edges, but it spans 3 meters in either direction. So the cornerstone is held up on 3 supports. The 4th corner is stable. The next stone is built in, and that takes its support from here and here, and it takes its support from the corner of the previous stone, etc., etc. So it's a kind of kinetically constrained structure. It's 40mm thick. It spans 3 meters under residential floor loading. So we're able to make an unreinforced stone slab. We built it in an hour in a museum. It's upcyclable, reconfigurable, very, very low carbon. So the equivalent in concrete would be a kind of 150 mil, 120 mil composite deck with a massive carbon footprint. So we're speculating from this that you can make a kit of parts. So using all the technologies that we've been kind of working with, so columns, beams, backed, post-tensioned. Rather than a cement lorry, you deliver a load of stone to a site, you build the columns and the beams, and you build the slabs in that way, and you can build a big, low-carbon, completely stone, upcyclable structure. So this was a small prototype of that in the building centre. Which has really dangerous cantilever. And then more recently, we did the stone exhibition in the building centre. And this was a 12-meter span reinforced post-tension stone beam. The idea was we build a 30-story office building for a city corporate column-free use. That we're looking at a kind of long span solution. So these are beams with a composite plate, completely limestone, built very quickly, not massively expensive. And interchangeable with precast concrete. I think it's very kind of interesting that when they first built steel structures, so the iron bridge in Telford, when that was built the first time, detailing of the iron, cast iron, looks like timber. So they're kind of mortise and tenon joints with little wedges. When Owen Williams, kind of engineer, architect who did Boots, Sweats and the Express building, when he was working with Maxwell Ayrton on the Empire exhibition at Wembley Stadium, he was getting very frustrated that Maxwell Ayrton wanted everything to look like stone. So they wanted concrete to look like sort of neoclassical stone structures. And he thought concrete needed its own language. And I think CLT to some degree emulates flat slab concrete. People are comfortable with the idea of the thickness of the CLT being a bit like the thickness of concrete. And I think here we're emulating concrete with stone, which is kind of ironic. We're making what looks like a precast concrete beam with a stone element. I think with modern methods of manufacturing and analysis and more sophisticated ways of quality control and quarry extraction using solar energy or wind energy or whatever, there's quite a big future for stone, but actually it won't be the stone that we used before. It'll be a new kind of stone, a new language. And I think these experiments, they're all kind of emulating different types of pre-existing structure. But I think stone could be a really fresh field where we actually, where little by little it's going to find its own architectural language that won't look like what it looked like before. So, I mean, this is a final slide, but black basalt is very, very strong. And these are kind of Wedgwood carved black basalt urns. There's lots of basalt out there. Buildings can be made of this material in an environmentally friendly way. Basalt's almost as strong as steel in compression. Reinforcing it for tension has huge scope, can be really kind of fresh. Sustainability tends to have a kind of, tends to sometimes look for a sort of atavistic or kind of hokey expression, whereas I think actually stone could be quite liberating and quite futuristic. Let's see what happens.
Thanks so much. Can we get a round of applause for Steve, please? Great. Steve, you have some questions. I'm going to put them to you now. But thank you very much. It was really interesting and amazing to see some of the projects. One is a really simple question. Sabrina Sufter wants to know from Brent Council, the reference to the concrete flooring and timber roof with negative embodied carbon. What project was that?
It's Wimbledon College of Art.
There we go.
It's a University of London project. For Noir and Prasad.
Magali Thompson from Great Ormond Street Hospital would like to know about your experience of using timber in hospitals. It has many therapeutic qualities, she thinks, but infection control issues seem to get in the way of it being used. So do you have any experience of the use of timber?
Yeah, I don't know anything about infection control, I have to say. I don't know. I mean, there must be timber in hospitals, right? You must be able to treat surface of timber in some way that would make it impermeable. I think, I know a psychologist friend of mine says that we feel parasympathetic around timber. It makes people calm because over centuries we think timber gives shelter. And when we did the Anna Freud building, it's for quite troubled kids, and they were saying their behavior improved a lot in the building surrounded by timber. So I think hear a lot about this, about the idea that I guess through a process of evolution, people that didn't feel good around timber or in caves with stone probably got eaten. So might be why.
Okay. Well, I know this is from my reading, Magali, you might want to look into the cutting board studies. There's some really interesting cutting board stories around in butchers' blocks being replaced by plastic cutting boards, and the way that bacteria tends to die on a wooden cutting board where it doesn't. So I think there are some interesting things out there around that if you look more into food technology, which might be interesting for you. Kathy Gibbs would like to know, have you had any interesting challenges or discussions from planning authorities? Certainly there was an interesting planning story around the Taha Stone building, but in this case, she's referring to building regulations and with respect to fire safety. And if so, how have you addressed them? And maybe with that question, you might want to pick up the kind of post-Grenfell approach to timber.
Yeah. So we've done a lot of timber buildings, CLT buildings, and there's been a sea change in the way they're examined post-Grenfell compared to pre-Grenfell, and there's obviously a lot more regulations surrounding how tall you can build it. And I think rather the Ronan Point disaster in the 60s that was a collapse of a prefabricated concrete tower block gave rise to the disproportionate collapse regulations in the UK building regs, which are kind of imprecise and a bit sloppy and reacted to that emergency, in a way that, people kind of struggle with the clarity of disproportionate collapse regulations today. It's quite, and I think that the response to the Grenfell thing has not been very clear. There's a lot of confusion about what is and what isn't allowable. They say the cladding can't have combustible material in it. Combustible under what circumstances? Is an internal wall cladding? At what point does a column become structure or a wall? It's not very clear. But yeah, we've had a lot of re-examination of fire performance of timber. How quickly it burns, whether it delaminates in a fire, how many exposed timber surfaces are facing each other. So we're just starting on site with a Mary Duggan office building and it's sprinklered. We had to limit some of the exposed faces, so all of the soffits of the office building are exposed, but we couldn't have soffits and walls exposed. The walls were okay in timber, but not the facades. And it was a struggle because people are not, fire engineers are very cautious, but they don't have the information to back them up yet. But I really think if we kill off timber construction in buildings as a result of needing to improve fire regulation of timber buildings, then it'll be a bad mistake from a sustainability perspective. I think we all have to kind of stick with it, push through this thing, and make work with timber suppliers and manufacturers to get the testing in place that justifies it. So I think timber is okay in a fire. It chars, it self protects. In many ways, it's better than steel. I think we shouldn't veer away from using timber because of those problems, because otherwise we'll create an even bigger problem. The bigger problem is sustainability.
Cost is often made to be an issue, is another question from Magali. Would a hybrid timber and concrete structure cost more than concrete only?
I think what we find is CLT is slightly more expensive than concrete. But if you take away the finishes and you expose the CLT, then the cost is comparable. Structure's not a massive, structure's like 20% of the cost of a building. In a hospital, I guess structure's like 10% of the cost. Maybe to make the structure sustainable, the structure costs 10% extra, so you've got 1% extra on your project cost. You could save 1% somewhere else. I think the more we use timber, the more. I mean, the issue is it's the industrial inertia of the concrete supply chain. All of the factories and machinery and plant and everything is there and is continuing to be produced, making it more economical. So the kind of outsider technology is always, more expensive in the beginning. But I think the more people, I don't, the costs aren't that different, and there are a lot of CLT manufacturers out there that can So you get competition and you get plurality of supply. So yeah.
There was a question from Kevin Fraser from Faulkner Browns. Do you think that stone would ever be mass produced as a building material when mining is generally frowned upon as being bad for the environment and costly in comparison to other material production?
Yeah, so basically everything is mined. Concrete is mined, steel is mined. Steel mines are, massive. South America, Australia, whatever. Stone is available locally. As I said, the volume of stone to build all the buildings in the world would be a quarry the size of Ben Nevis. It's like one for the whole world. If we built everyone's houses today, it would be one tiny mountain. So the volumes are tiny. Forestry is not that great, really. There's, if you walk around Scotland, forestry is not a great thing for the environment. It takes up a lot of space. Agriculture, you dig a quarry, you return it to nature afterwards over a short period of time, and it's a lake with some trees, whatever. It's not, and it's non-toxic. You're not producing loads of nasty chemicals. You look at what wheat production does to the UK countryside, forestry does to the Scottish countryside. Quarrying, you hardly ever see a quarry. It's not, and all building materials, all the concrete comes out of the ground, all the steel comes out of the ground. It's not that impactful.
I think in terms of that sense of, kind of where do you see the gaps in getting that message across, to a wider audience? Is there a lack of political understanding, or, when you think about your professional challenge, what is your professional challenge in with regards to getting this stuff built? And
I think, we don't. Yeah, so we do a little bit of R&D. We have no R&D budget, really. We spend like $3,000 a year, and we sit there with a pencil and paper and try a few things. So there's no serious effort on our part to do R&D into stone. We do it because it's fun. But in Germany and Austria, when they started the CLT thing, they federated lots of companies. The government invested in it. It was an organized, systematic assault on the concrete market. Come up with a good product, make a load of factories there, and start marketing it and selling it. And it's organized and it's done on a large scale. That they intervene to bring that new industry to fruition and create a lot of employment and create those things. I don't see, nobody's phoning me up saying, could we do this with stone in the UK, for example? Or I don't know. The UK is just not, has a far more laissez-faire attitude to industrial development and just wouldn't intervene in that way. But at the same time, the stone industry is, it's really a decorative bathroom tile industry. It's just not run along those lines. So it's kind of an odd thing. I would love it if somebody came along and said, we're going to build 5 factories and spend 10 billion on R&D and everything's going to be,
Well, I think it's interesting if it's like if you put £3,000 into R&D, have you ever thought about federating with other architects and engineers to create a larger R&D budget together?
Yeah, we do. We work with different manufacturers and some different people. I think, but it's kind of. It's a slight problem in the UK in general. If in Italy you own a factory, you're a classy chic person doing an interesting job. In the UK, if you own a factory, it doesn't have. So you get a lot of people who end up like me, consultants. I would love to own a factory. I think be a highly kind of honorable and interesting thing to make stuff, rather than be a consultant in an office. And I think that's sorry, I'm getting totally off the point. I think developing a product and selling it as an industrial entity is a great and interesting thing to do. And if somebody wanted to do that, I would be really happy to. We're kind of doing it with the stonemasonry company, but to actually shift the center of gravity from concrete to timber has required a lot of time and a lot of money and a lot of, a pretty large scale intervention. So to get stone to the point where It's so simple. You dig the stone up, you drill holes through it, you lace it together, you pre-stress it, you stick it on a truck. I mean, it's a no-brains, easy process, to make to make a stone beam factory compared to the processes. So I go down to somewhere in Cornwall, granite, I dig up stone blocks, I drill holes through them, I put a tendon through, I post-tension it together, I stick it on the back of a truck, it goes to site. I dig up iron ore in Brazil, I ship it to China, I put it through a blast furnace, I bring it here and I re-blend it, and then I roll it, and then I weld it, and I fabricate it, and I do all the stuff to make a steel building, it's insane, People say, oh, what's that, what are the practical logistics of stone, well, compared to something that has to be delivered in a rotating tank on the back of a truck, pretty good,
You made a kind of passing comment, brick is not sustainable, but we had to use brick for context in this project. First of all, can you explain if there is such thing as a sustainable brick, or why brick is not sustainable? And second of all, do you want to comment, because brick is something that planners like quite a lot?
Yeah, biscuit buildings, New London vernacular, concrete frame buildings covered in bricks, not environmentally friendly. Bad. And boring. Why are we using brick? Why are we using brick in London in the first place? We use brick in London in the first place because the clay was under our feet, and because we could bring 10% of the volume of clay from Newcastle, open coal mines, bring it here, burn the clay, make the building. It saved us time and money in an age where there wasn't availability of transportation. And brick was built thick. It's better than, more sustainable as adobe or cob, which has to be much thicker, so you save a lot of time by firing the clay bricks and making a thinner wall. Nowadays, decorating, and a brick is the size it is because an Egyptian laborer can keep putting one brick on top of another all day long without his arm hurting. That's why a brick is this size, or can be carried on a hod, like the site. It's a building, decorating buildings in brickwork. It's as absurd as us driving around making our cars look like fiberglass steam engines. I think absolutely ridiculous building in brick. Somebody told me we were doing a tower for a housing company, a 15-story tower. I was saying, well, look, if you really want it to look like brick, it's better not to have 1,000 tons of brickwork hanging in the air and all of the energy and structure that requires. So we should just clad it in tiles. It's going to be much better. Oh, no, we want proper brickwork. What's proper about 100 millimeters of a decorative finish stuck on a building with stainless steel, shelf angles, wind posts, ties, clips, all of the crap that goes into making brickwork? I mean, and brick is weak. It expands when it's wet, it cracks, it shrinks, it needs repointing, it's like, our obsession with brick in London is, and it's a coal age, brick is of the coal age. This energy historian Barnabas Calder was saying, it's like we're celebrating something which has put us in a sustainability mess, it's a coal age product, and dumb. Why do we keep doing it? Don't understand.
I sometimes will interview a developer, an architect, and they'll tell me how they flew to Denmark to choose their special coal-fired Danish hand-struck brick. Because they feel it's beautiful and aesthetically very pleasing. So the response to them, I think, has been fairly clear, that this is a ridiculous thing to be doing.
Yeah, I mean, things can be beautiful in many ways. They don't have to be beautiful just because they're made out of brick, It's like, it's just not, the only beautiful thing I could think of was brick, so I ruined the environment. Great. Very clever.
We have just one question left, and we have just but we just have 1 minute. So very quickly, have you come across any difficulties with justifying stone as a building material when trying to achieve progressive collapse requirements? What's the most suitable way to tie the stone to the frame?
Yeah, so in the Clerkenwell Close example, disproportionate collapse. So if there's a gas explosion inside the building and it blows out the column, not so much of the building, or you have to limit the amount of the building that can collapse. So we worked out that the stone piers were strong enough to withstand the gas explosion, and there was enough friction holding them in the building to stop them from being blown out. So untied brick design is a key element. Untied stone, sorry, brick, not brick, stone. Quite surprising that worked. But yeah, you can tie it together. You can reinforce it. You can put bars through it. There's lots.
It sounds like not brick stone is it was the alternative title for this talk we probably should have come up with. I should say that question was from Richard Dowdell from Civic Engineers. That just leaves me to a round of applause, please, for Steve. Thank you very much for doing the talk today. Really, really enjoyable. Great to get your frank view on material specification. I think often we have these conversations about sustainability, and actually, I think what's really refreshing is you put it in a kind of way that we can understand it very clearly. Not a lot of mystery, just a lot of common sense, and actually a lot of practical and tips and skills. Great to see some projects there and some of the work that you're doing. So thanks very much for coming to the festival today.
Thank you very much. Thanks for inviting me.
So we are back at, we're back with the pineapples, just coming up quite soon. We've got a great presentation. We've got King's Cross is going to be presented, and we've got Aberfeldy and Brooklands Square coming up. So don't miss that. That's at 12:15. And then at 2 o'clock, we've got an excellent workshop with Tim Gill, super popular last year, definitely worth checking out as well. Forget risk. What about a benefits assessment? And Tim's going to be helping you, as opposed to becoming a risk averse, to become a pro-benefit developer and designer. So do come and check that out at 2 o'clock. Thanks so much, Steve.
Okay, thank you.
Bye.